Hi, in this video we are going to go through an overview of the solution for part 1 of LAB1. I'll probably do it in chunks because I attempted to do it all in one go late last night and it didn't go so well. So you might find that it chops in and out from certain sections. Okay, so the first thing I want to look at is the actual task as a block diagram. Because a lot of people seem to be getting a little mixed up with where the registers exist in the slave with the registers that exist in the processor. So I have this very basic diagram which I'm just going to annotate. So the outer block is the FPGA chip. Okay. Within the FPGA chip, we have a QSys module. This is neos_system. And we have these two outside Verilog modules. Okay, we'll get to those later. Within the Neos system, you have a Neos processor, which connects to this Avalon bus. Okay, so there's a connection here. And the Neos is the master device on the bus. So it will control transactions between itself and slave devices from that, from using that bus. So one of the slave devices that is also connected to that shared Avalon bus is the on-chip memory. And that is where the instructions for the Neos processor would be stored. And then the other slave device that we have is the external bus bridge. And what this is doing is it's allowing a connection from the Avalon bus externally from the Neos system. So within that Neos system, there is an address assignment to each slave device, and the address assignment for the external bus bridge has been set from 0x0 all the way to 0x7ff. Okay, so that means if the Neos processor was to do any store word or load word or store or load transaction to an address within this range, then it would be accessing whatever is connected to the external bus bridge. So there is a connection out of the Neos system to this module here via the bus bridge. And this is your peripheral module. So the peripheral on external bus. And within that peripheral, you have these 4 memory locations that we are calling registers. So these are the slave registers. Okay. You then have this other module on the left, which is this 7 segment display. And all that does is it takes, so there are connections between these two modules. Right, well actually it's only one way. So it's just connections going this way. And we also have 2 switches, 1 and 0, which are external to the FPGA, which provide input into here. So based on those 2 switches, the connections here are from the actual direct registers within that peripheral block. So depending on these 2 switches, it's going to choose the 16 bits of one of those registers, it's going to do a conversion. So we'll have some module in here, binary to hexadecimal, or binary to 7 segment, whatever. Call it binary to hex. It will take that value and then it will pass it out to the actual 7 segment displays on the DE2 board. Okay, and there are 8 of them. Okay, we'll only be using 4. So to go back to when the NEOS processor wants to access one of these slave registers, let's say it wants to write to it, it needs to do some kind of store operation. So it might do a store byte, and then you'll have some register value and then an address. Okay, so let's say, so the address that's in here needs to be within this range for it to indicate to the Avalon bus that it needs to go to the external bus bridge, which then passes it out to here. And then the peripheral module will decide which of these 4 registers it is mapped to. Okay, and which of those 4 registers it's mapped to depends on what the address decoding is implemented as within this peripheral module. Okay, so that's all I wanted to discuss about this particular block diagram and how the access is. So I'm just going to exit this now and go back to here. Okay, the next thing that I want to look at is the actual implementation of the peripheral on external bus module, which is this one here. So this module is a slave device that will respond to requests made coming through from the bus bridge. So the inputs coming from the bus bridge are address, bus enable, byte enable, read write, and write data. And the outputs that the slave responds with are acknowledge and a read data value. You're also outputting these 4 register values that will go to the hex 7 segment display module to display on the 7 segment on the DE2 board. Okay, so the sequential logic here implements the reset and the write logic. So on an active low reset, you will reset your registers to some values. So I have changed the defaults from 0s to 0s, 1s, 2s, and 3s. That will help when running on the board and trying to debug it. Then if it's not a reset, it will then check are the bus signals valid? So that would be when bus enable is 1, and is it a write? So when RW is 0, that's a write transaction. Then we have the address decoding section, which is all of that. So it looks at the address values. What are the top 2 bits, and we chose this because we wanted to equally divide the whole address space into quarters. So it checks, are the top 2 bits 0, 0? That means you are in the first quarter of addresses between 0 and 1 FFFF. So the address is somewhere in there. If that is the case, then we want to be accessing register 0. So we're mapping that first quarter all to register 0. The next thing that it checks is if the byte enable 1 is on. The byte enable 1 refers to the upper byte. If that is on, then you want to take the upper byte bits from write data and put it into the upper byte bits of register 0. And then a similar if condition for byte enable 0. If that's 1, then you put bits 7 to 0 into 7 to 0. Okay, and the rest are similar conditions, but obviously changing the bits on the top 2 and accessing a different register. Now, this particular implementation uses nested ifs, so an if statement within an if statement and so on. Another option that you could have done is had a case statement for this, for the address bits, and within the case, the different cases in the case statement, you could have nested if statements. There are many different ways of doing it. It's up to you. Yeah, so the next part is just the acknowledge. So the acknowledge is just equal to the bus enable. And that, like I told you in the lecture, was because we're assuming that this slave device can complete its transaction. So it can complete the transaction very quickly. And it should be done by the end of the clock cycle. So as soon as you see the bus enable high, you can just set the acknowledge high. And by the next pos edge, the processor knows that the transaction is done. And then the last part is setting read data. So read data is just a simple combinational logic assignment, which just checks what the 2 bits of the address 18 to 17 are, and then assigns read data to the corresponding mapped slave register. Okay, the alternative method that you could have used for this was an always block. So we'll just comment this out, or uncomment, sorry. So you could have used an always block where you did a case statement based on the 2 bits of address, and then you would assign read data according to the case. Now, if you did it using this method, then read data would need to be declared as a reg, because in always blocks you can only give a value to a reg, but currently it's declared as a wire. It's declared as an output, which defaults as a wire. So if you wanted to change it to a reg, you would just type reg there. And now if you make it a reg, you can't assign to it outside of an always block. So you couldn't do this once you make it a reg. Anyway, let's comment that back again. All right, so that was the peripheral on external bus. Now, some of you were asking why we chose these bits. Like, couldn't you choose some other bits? Couldn't you choose address 2 to 1 or something like that? Or even put a specific address, a completely specific 19-bit address equality here? You could do that. There are different ways you could have done this section. We chose to do it this way, or I chose to do it this way because I thought it was the simplest implementation, and it covers all possible addresses within the external bus bridge address range. Although it does assign a wide range of addresses to a wide range of contiguous addresses to the same register. So that means if you write to, say, address 0 in one transaction, and then you write to address 10 in the next transaction, because of this size of addresses mapped to this register, it would both write to register 0 in this slave device. Okay, let's save that. The next thing that we want to talk about is the 7-segment display module. Okay, so the inputs to this are the 4 16-bit registers, which is coming directly from peripheral on external bus. You can see that in here, where you have these are an output, which get connected directly to these inputs. Okay, And then you've got these 7-bit outputs, which would be connected directly to output pins that go to the hex displays, which are off chip. So within this, what I've done is I've first assigned all ones to the display outputs 4, 5, 6, and 7, because we won't be using them, because you only need 4 7-segment displays to show a 16-bit value in hexadecimal. I've then used a similar ternary statement to assign this wire called selected reg, and what that does is it checks this register selection input, which, if we go back to here, is connected to the switches 1 and 0. It checks that value, and depending on what it is, it will assign one of the 16-bit registers to this wire. Okay, that wire is then used later on to do the binary to hex decoding. So once again, an alternative method that you could have used to do that is this always block, which looks pretty much the same as what I showed you in the other module. Okay. And then the final thing is 4 instantiations of this module called bin to hex, or binary to hex, which is defined here. So what this does is it takes in a 4-bit input, which will be your 4-bit binary value that you want to display as a hex digit. It then does an always block that will check what the input value is, and depending on what it is, it will set the output to a 7-bit value that will draw that particular hexadecimal digit on the display. So the 7-segment displays on the D2 board are active low. That means a particular bit, if it is 0, will turn on that particular segment. So I have defined this as 6 to 0, which means that this bit here is going to be the element 6 on the hexadecimal display, and this will be element 0. And just to explain what the segments numbers correspond to, maybe we'll just go back to PowerPoint, and I'll just draw on here. So your 7th segment will look like this, and each of those segments is assigned a value, a number or a bit. So this will be bit 0, 1, 2, 3, 4, 5, and 6. So if we are putting them from bit 6 to bit 0, then let's say we wanted to draw a 3. Oops. Okay, so we want to draw a 3, so we want these segments to be on. And because it's active low, that means a 0 bit will turn it on. So we want segment 0 on, we want segment 1 on, segment 1 on, we want segment 2 on, segment 3 on, then we want segment 4 off, segment 5 off, and segment 6 on. So this pattern here would draw a 3 on the hex display. Okay, so that is how I came up with this whole table. So you just go through and you do that for each of the different cases, and then you get it. So once you create that module and instantiate it 4 times, what you are doing is for each of those instantiations, you take a small 4-bit chunk of the 16-bit selected reg, and then you output it to a particular 7-segment display. So I've taken the bottom 4 bits and they will go out to 7-segment display 0, which is then connected out to hex 0 on the D2 board. Okay, so that's the whole 7-segment display module. So with the top level module, you didn't need to change anything. You just needed to check that this instantiation was correct according to your NEOS, your QSys setup. All right, so the next thing that I want to go through is how we test whether the peripheral on external bus module is working correctly using the test bench. So you need to make sure that the test bench is added to your file list. So this is the test bench that I provided, peripheral_test bench. You need to make sure that it's set as top level entity. So it appears up here. You also need to make sure that you are in RTL simulation mode. Okay. In the test bench, what's happening is that you instantiate the peripheral on external bus module here. You would have a number of registers for the input lines, and those registers are going to be assigned, or the values for those inputs will be assigned from reading values out of this file that is opened here. And then you have wires for the outputs, which come out of the module. So in this initial block, we set initial values. So the clock is assigned to 1 and the reset is assigned to 1. And then you open this file. So let's start off by changing the text file to the bytes and the short test. Okay, so in that file, it's just a number of lines. So maybe we can actually open that file and show you what's going on there. Okay, it's just a number of lines that have a set number of values in each line. Okay, and these values correspond to certain signal values. So I created a Python script that generated all these values based on a predefined set of instructions that I wanted it to complete. Okay, and I've made it generate it such that each of these lines corresponds to 1 nanosecond of values. I didn't need to do it that way, but I just did it so that I could simulate some logic gate delay that is variable. Anyway, so in the test bench, what happens is it once it's opened the file and initialized the values, the clock signal in this always block is going to oscillate every 10 nanoseconds, so that makes a 50 megahertz clock. And then in this always block, on every nanosecond, it's going to read in those values from the file, or a line from that file, and assign them to the input registers that feed the peripheral test module here. Okay, and then it will keep doing that until it reaches the end of the file, in which case it closes the file and it displays the total amount of errors that are counted throughout the simulation, and then it stops the simulation. Okay, so in this always block here, which is triggered on every pos edge of this clock signal, so it should be every 20 nanoseconds, what it does is it checks certain signals against the expected signals that have been read out of that text file. So here it checks, is the acknowledge not equal to the expected acknowledge value? If that's the case, then display an error showing the time, the expected value, and the actual value it got, and increment the error count. The second if statement checks the read data. So first it will look if read write is 1, that means it's a read operation. Then it will check what the byte enable situation is. So depending on what the byte enable bits are, it will test slightly different sections of the read data. So if you're just writing 1 byte and it's a lower byte, or reading 1 byte and the lower byte, then it will check the lower bits of read data. If they're not equal to the lower bits of expected read data, then it will throw an error and increment the error count. The same for the other ones, but obviously different bits that are being compared. Okay, where was I? So yes, so what you need to make sure is correct in this test bench. One, the path to the file. Make sure you are using / and not \. And then make sure that the instantiation matches the module that you use. So in my module, I've only got CLK and reset N here, but I think in most other modules, I think in the template, it's clock _clock and reset _reset N, which is why some of you might have to have changed it. Anyway, so before we can actually run the simulation, you need to make sure that you've set up the model sim settings. So under tools, options, make sure that you've chosen that path here. See, or what will be in your Altera folder, 13.0 Service Pack 1, Model Sim ASE, and the folder is Win32ALOEM. Second thing that you need to make sure you've done is in assignments settings. Make sure that you've done under EDA tool settings, simulation, make sure you've set Model Sim Altera and Verilog here. Okay, so now we run the analysis and elaboration. And then we double click on RTL simulation, which should now open up Model Sim. Okay, once Model Sim is opened up, you should see that there is a work section in library. So we need to double click on peripheral _ test bench because that's the name of our test bench. We can select the signals we want. So I usually leave out the file signal, and then we can drag them into this wave window. Now to run the test bench, we click in the transcript window, type run-all and press enter. And that will run the simulation, and then when it reaches the stop, it might open up this .v file. You can just close it there. Then click in the wave window, and if you want to zoom out, you can choose zoom full, which zooms to the whole range of the simulation. Then what you can do, open this out a bit so you can see what the names of the signals are. You can highlight all of these, or at least I like to do this. Change the radix to hexadecimal so that the values are a little easier to read. And then what you can do is you can inspect values at a particular time instance. So wherever the yellow line is, all the signal values at that point in time are shown here in this messages column. So you can move across to a certain section just to check what the values are. So you should have been looking at this a little bit to understand what kind of bus transactions were being generated, what were the signals in those cases, and what was happening on, for example, the acknowledge and the read data and the register values. Okay, so that was running the bytes operation, the bytes and the short test. So if you wanted to change which particular test file you were using, you just rename or change the path within here. So if we wanted to do the long test and maybe for half words, obviously you would need to make sure that you have downloaded these files, save that, and then you run the simulation again. So you should really be testing all the test files to make sure they all come up with no errors. Oh, actually, that was what I forgot to talk about. We didn't look at the display at the bottom, which showed if there were any errors. Okay, so this test is longer, so it will take longer to run. Okay, so if we zoom full, you see that you see a lot of green, and that's because there's a lot of transitions within that time instant. So you can zoom all the way in, and then if you wanted to change the radix to hexadecimal, then you can see some of the values. Okay, so these are doing transfers of half words. So if you had any errors, they would be displayed down here in blue. This one has ended up with no errors. Now, something else that a lot of people might have come across is red signals in some or most of their simulation. And that could mean that you have some issues in your logic, but most of the time what it meant was that there were undefined signals from the beginning of the simulation. So it meant that it wasn't given an initial value, and therefore it was undefined because it was never assigned to later on. So to solve that issue, what you needed to do was to give the registers an initial value in your peripheral module. So in here, when you create these registers here with this declaration, if you just say equals 16D0, you give it an initial value. The next thing that we will do is actually test the configuration on the actual D2 board. So in order to do that, we need to do a full compilation. So we need to set this to top level entity, lab10 underscore part1. We need to change over to full compilation mode. And then we need to run the compilation. Okay, now that the compilation has completed successfully, we can program the D2 board. So we open up the programmer tool, and then we'll make sure that the project name.sof file, so buscom.sof, is selected here. And then the USB blaster, which is the connection to the actual D2 board, is selected, and then we can click start. So when I click start, you should see on the D2 board that the load light will turn on, and then once it's finished, it turns off. Okay, so what you should notice now is that the leftmost hex displays are off and the rightmost hex displays are zeros. So the switch values 1 and 0 are 0, 0. So this value should be showing slave register 0. If I move the bottom right switch up, so now it's 0, 1, so it should be showing register 1. But as you can see, the value is 0, and the same with register 2 and register 3. They're all showing 0. That is because we put in, or I put in these zeros here to initialize it. Now I also put in this register, this reset condition, where if reset is active, it should reset all the registers to these values here. So if I was to press the reset button, and then now I go to register 1, it's all 1s, register 2 is all 2s, and register 3 is all 3s. Okay, so that tells us that at least this reset section is working, and so is your 7-segment display module. Okay, so now that that is working, the next thing that we have to actually check is whether you can, or whether we can actually access the registers via assembly, which means that the NEOS processor is actually accessing the slave registers. So I've got this assembly code here, which implements the part 1 assembly operations that are required. And so what we do here is first load registers with the addresses that map to the different slave registers. So I've put in the first address in the range for each register. So 0 is the first address that is mapped to register 0 in the slave. And then that mapping, or the first register, will have all the addresses from 0 all the way to 1FFFF, which is 1 less than this. And then 0x20,000 would be the first address mapped to the second register, and then so on and so forth. The last address, 7FFFF, is the last address that is mapped to register 3. So I'm putting that in as well so we can test that boundary, that corner case. I'm then storing different 16-bit values, 1s, 2s, 3s, and 4s into these 4 registers. So all of these registers are the processor registers, and the address is mapped to the slave registers. And then I start off by trying store byte first. So I will store byte the value of these 1s into the first slave register, because that address maps to this first slave register. Then I will use a load byte to load it back out from that slave register into processor register R11. Then I will do another store byte, but this time to an odd address because I put an offset of 1 here. And then I'll read it back as well. So that will check the byte enable functionality for the 2 different possibilities of byte enable. Then we will do store half words. We're doing all 4 in a row, where each one writes to different slave register, and then 4 load half words, which each reads them back into different processor registers. And then finally we do a store byte to the final address mapped to register 3, and load it back. So that is our .s file that we'll be using. So what we need to do now is go to monitor program. We need to create a new project. And then navigate to the folder that contains our Quartus project. And then what we can do is we can create a monitor folder here. And we'll just call this lab part 1 for the project name. So over here you need to select custom system because we've defined our own system that we configured on the FPGA. We need to choose the QSys file here. So the QSys file will be neos_system.qsys. And then you need to choose the programming file here, which is the .sof file, which will be in the output files folder, buscom.sof. Then we click next. The program type we're using is an assembly program. And then we can add the .s file. So I put that .s file here. Then we click next. So on this page we need to make sure that the USB blaster shows up. You can see a processor name here and a terminal device. And you can just leave that as default. Okay, so what this will do is it will prompt you if you want to download the system to the FPGA. Now we've already downloaded the system using Quartus in the programmer, so you can skip this step if you want. So we'll just click no, but there is the option of clicking download system here to do the same thing that the programmer does in Quartus. Once we're in here, we can compile the .s file. Okay, and that compiles successfully, and then when we click load, that would load the compiled machine code onto the processor that's on the FPGA. And then you can see that there's a disassembly of what's there. Now, unfortunately, the resolution of this is really bad. The font, I can't really change that. So maybe you can, I don't know, squint. Okay, so we will step through this and then we'll see what's going on. So the first things that happen are that it stores the addresses. So you can see them popping up in the right here as I step over. You'll notice that this looks very similar to the CPU later simulator online. So we can keep going until we've loaded all the addresses and all the values that we want into the processor registers. And now we're at the first store byte instruction. So this store byte is going to store into address 0, which is the memory mapped address. So once we do that store, we can actually, in this memory window, if we were to query all devices, now currently the register 0 on the slave is showing all zeros. So once we do that store byte, we should expect that in this 0 address here, it would show 1 1 in the first 2 digits. Now, because all of these addresses here, all the way up to 1FFF, are mapped to slave register 0, we should see that there will be a recurring pattern. Even though we write to just this address, we'll see it happen across all the other ones, because what's happening here, to get these memory mapped values, the processor actually does a load out of the addresses that it thinks are mapped to these memory values. I'll just run it and we'll see it make more sense. So the other thing that should happen when I do this store byte is that you should see that the bottom 2 hex digits here should become 1. Okay, so I stepped over, we can see on the hex displays they're both 1, and then when we go to the memory window we can see this recurring pattern of 1. So it wrote to this address here, which mapped to slave register 0. But slave register 0 is going to be the same for every half word increment. So this is the first half word, and then the next half word is here, which is the same, and the next half word's here, and so on and so forth. So that should repeat all the way up to just before 20,000. So if we go to address 20,000, scroll up a bit, you see that that pattern repeated all the way up to here, and then at address 20,000 we start the next slave register's values. So if we switch over to slave register 1, you can see that it's showing all 1s, which is why it's there. So on slave register 3 it's showing all 2s. So if we were to go to 40,000 we should see all 2s, and so on and so forth all the way up to 7FF. Okay, and that's 3s, which is the last one there. Okay, so let's go back to 0. So the next thing that we are testing is loading it back. So we use a load byte and we're going to load it back into R11 on the processor register. So we can do step over that, and now we see 1 1 here, which is correct. Okay, the next store byte will load into the next byte address of the first slave register, because it's an odd byte. So what we expect to see is that these 00s here will become 2 2, because R8 holds 2s. So that became 2 2, that's correct, and we can also see it in the memory window where it's now 1 1 2 2, and that repeats. But once again, if we go to 20,000 here, it's still 1s, which you can still see here, 1s. Okay. And then it will load that value back into R12, and that worked fine. So that was verifying that that worked. Now, to verify 16-bit transfers, we're going to do store half words and then load half words back. So first we're going to do a store half word, and each of the addresses used is going to be mapped to a different slave register, because we've put the addresses at the start of each of the slave register mappings. So we will do all that. So this should write 1s to slave register 0, then I'll click it again to step over, and 2s to slave register 1, and then 3s, and then 4s. Okay, so we have 1s, 2s, 3s, and 4s. Okay, so now we're going to load that back out with a load half word. Okay, so that was all 1s, so that's correct. 2s, 3s, and 4s. And then the last thing that we need to do, which I just did there, was I did a store byte to 7FFFF. So if I go to the memory window, 7FFFF maps to the last slave register, but it also maps to the upper byte in the last slave register. So it's actually this address right here, but you see that it's also a recurring pattern. And if we go on the board to 3, we see 2244 there on the D2 board. All right, and then the last thing we do is load byte back. and that's stored in R22, the value 22. Okay, so that was the process you should have been using, or the kinds of instructions that would test most of, or pretty much all of the functionality. It doesn't test all of the addresses in the range from 0 to 7FFF, but it tests the minimum number to be able to check the different slave register mappings. And we test all types of transactions except for word transactions. The reason for not being able to do the word transactions is because if you have contiguous addresses mapped to one particular slave register, that means if you do a word transfer, it's going to do two 16-bit transfers to two addresses that are next to each other, pretty much. So it will first, let's say you are doing a word transfer to address 0, it will first write 16 bits to address 0, which is going to map to register 0, and so now that will contain the 16 bits that was first written. Then it will write another 16 bits, which is the upper 16 bits of the word, to address 2, and address 2 also maps to register 0. So now that 16 bits has overwritten what was originally there. Okay, so that's that. What I wanted to cover last was a different address decoding. So what we might do is close monitor program first. Then we will, I'm just going to stop the recording on the camera. Okay. So what we want to do is try another option for this address decoding. So instead of using the top 2 bits, what we can do is use the least significant bits, but not the most least significant bits. We want to use bits 2 to 1, because the least significant bit is always going to be 0 of the address, because each half word is going to start at a multiple of 2. So we can ignore the bottom bit and we can use bits 2 to 1. So we'll replace this with 2 to 1 in all these locations. And so what this now means is that if these 2 bits are 0, 0, it's going to be mapped to register 0. And then if it's 0, 1, mapped to register 1, and so on and so forth. But if we were to write that out, what that would mean is if we're address 0 would map to register 0 in the slave, then address 2 would map to register 1, and then 4 would map to register 2, and then 6 maps to register 3. But then what happens is that it repeats. So at address 8, it's going to be mapping to register 0 again. And then at 10, it's going to be mapping to register 1 again. And that will just go on and on. Now, the reason for that is because if you were to look at the binary values for these numbers, these address numbers, you will see why that is the case. So 0 is equivalent, if we were to just write out 4 bits, 0 equals that. So these are the bottom 4 bits of the address line. So 2 is going to look like this. And then 3 is going to look like that. Sorry, it's meant to be 4. So 4 is going to look like that. And then 6 is going to look like that. 8. Okay, so we have chosen to use address bits 2 to 1, and address 2 to 1 is these 2 bits here. So if we were to look at those 2 bits for each of these addresses that we've written down here, it starts off at 0, 0 for address 0. So that will go to reg 0 based on this logic here. Then the next thing, when it's 2, it's 0, 1, and then 1, 0, and then 1, 1. And then after this point, it repeats. So now that particular bit goes to 0, 0, even though the address is completely different. We're only looking at these 2 bits for the decoding. So it repeats again. So the pattern that you should find in the memory now when we do a write to reg 0, for example, is that you should see the value at address 0 and then at 8 addresses forward, and then another 8 addresses forward, and then another, and so on and so forth. So anyway, what we'll do is we'll save that and compile it. And so now we need to change our .s file slightly. So let's save this as part1b.s. And what I'm going to do is I'm going to get rid of the store bytes. I'm going to change these addresses here. So we will go from 0246 and then maybe 8. Okay. Yeah, so we will write a half word to address 0 first, then a half word to address 2, and then 4, 6, 8. So this address will still map to register 0 in the slave, and this register 1 and 2, 3. This one should map to register 0 again, because it repeats. Okay, so the compilation should almost be done. What I might do is turn on the camera again. Okay, so now we can program the device. Okay, and then we can go to monitor program. Oops. Okay, we can open up the same project that we made, LAB1, LAB1. We just downloaded the hardware configuration, so we don't need to do this. But we do need to go to settings, program settings, and then change this file to the part1b.s. Okay, and then click this to compile and load. Okay, and then we will step through. So we're storing 2, 4, 6, 8 for the addresses, 1s, 2s, 3s, and 4s. Now the first store half word should make register 0 all 1s. Yep, which it has done here. The next store half word should make register 1. Before we do that next store half word, let's go to the memory and check what that first store did. So it wrote to this address here, the half word starting at 0. So it wrote those 4 ones. Now I told you that it repeats every 8 addresses, which is every 4 half words. So 1, 2, 3, and then 4. So at address 8 here, it's repeated again, and then it's repeated again there and there. Okay, because they're all referring to the same slave register. But now instead of all of this referring to that slave register 0, it is now all of this column, these 2 columns. Okay, so the next one should update this to 2s, which it has. And then the next one, updating register 2 to 3s and register 3 to 4s. Now if we go back to the memory window, now you'll see that it alternates. So we've got slave register 0 first, then slave register 1, slave register 2, and slave register 3. And then slave register 0, 1, 2, 3, 0, 1, 2, 3, and so on and so forth. And that is how it alternates because of the new address decoding method that we used. The last thing that I wanted to cover was a quick discussion about part 2 in terms of the block diagram. So we can actually use this as a base, but now for part 2, the thing that we don't have is this 7-segment display. And this module here is now your SRAM controller module. The rest is the same. So we still have the red block being the FPGA, and then within that you have your NEOS underscore system, and within that QSYS block, which is NEOS underscore system, you have the NEOS processor, you have the Avalon bus, the memory, on-chip memory, and you still have this bus bridge, the external bus bridge. Okay, and that the memory space assigned to this external bus bridge is still the same as well, 0x0 to 0x7F. Okay, so none of that changes. Now the thing that does change is that what this is interfaced with outside of the QSYS block, or the NEOS system block, is this SRAM controller module in place of the peripheral module that you had in part 1. Okay, that SRAM controller acts as a translator between the Avalon bus protocol and a bus protocol that goes to the SRAM chip. So let's say the SRAM chip is here. So SRAM chip exists off the FPGA. And that has, in this case, we are accessing 512 kilobytes of memory locations in that chip. So to go into a little more detail about the conversion that this SRAM controller module is doing, let's just create a new slide. Okay, so we have the SRAM controller here. Okay, and it's got some coming from this is from NEOS system. Okay, it's got a bunch of signals that are the Avalon bus signals. So there will be address lines, which are 18 to 0. So there are 19 bits of address lines. Then there is a bus enable. And then a read-write bit. Then you have your byte enable bits. And then you have write data. Okay, so write data is 16 bits. Byte enable is 2 bits. And so all of these signals are going that way. Then coming back from the SRAM controller would be the acknowledge and the read data, which is also 16 bits. Okay, so these ones here are the Avalon what's going on? The Avalon bus signals. Now on the other end of the SRAM controller, we've got address lines, but now it's an 18-bit address. So this is going to the SRAM chip. Okay, so you have 18 bits of address lines, and now instead of a bus enable, you have a chip enable, and it's active low. That's what the _n means. You have a chip enable, you have an output enable, you've got a write enable, and then you have an upper byte enable, a lower byte enable, so all of these signals that have the ends are all active low. Now the only other signal that's left in the SRAM chip is the SRAM DQ. Now this is different to the Avalon bus in that it is a bidirectional line. Okay, so it goes both ways. Okay, so that's 15 to 0 as well. Now, for a bidirectional bus to be shared between two particular modules or devices, if one particular module is setting the value of that line, so for example, if we are doing a write from the processor, which needs to go this way, the SRAM controller needs to set the value of the SRAM DQ. So in that case, you would assign SRAM DQ equal to whatever write data is here. Okay, so in that case, on the SRAM chip end, what it would be doing inside that chip is it would be assigning the SRAM DQ to high impedance so that it would be able to read it in that case. But we don't know what's going on really in the SRAM chip because we are here. We are creating the SRAM controller. So when the SRAM controller needs to read from the SRAM DQ, which means the SRAM chip is driving it, it needs to set the SRAM DQ to high impedance. So when this read-write is a 1, that means SRAM DQ should be assigned to high impedance. And the read data would then be assigned to whatever value is on the SRAM DQ, which is not actually high impedance. What the value that gets put on there won't be high impedance. It will be whatever is being driven by the SRAM chip here. So if you have done the test bench simulation of the SRAM controller using my test bench, you'll find that read data will become high impedance in that scenario because there is actually no chip on the other end driving that SRAM DQ signal back in that particular instance. Okay, so now for the other signals, if it's not clear to you, then you need to, all of these signals here are simply just a slight differentiation of what these ones are on the left. So for example, chip enable is the same as bus enable, except this is active low. So that value should be should just be the inverse of bus enable. Output enable will relate to the read and write enable to the write, and the upper and lower byte values would somehow relate to byte enable on the Avalon bus end. Okay, then the last thing that's left is this address difference. Okay, I'm not going to tell you how to do that exactly in code, but what I will explain is why there's a difference there in the size of the address lines. Okay, so the NEOS system expects a byte addressing in the memory. So it is expecting that every location in memory is a byte. Each byte has an address. Okay, so this would be address 0, 1, 2, 3, 4, so on and so forth. And this width would be 8 bits or 1 byte. Okay. So if you wanted to write to a particular byte, let's say this one here, you did a store byte to there, what you would see on your Avalon bus address value would be the address of that byte in terms of the half word alignment. So that byte is even, so it just happens that that address will be 6. If we were writing to this address, then your address value would still be 6 because it is half word aligned. Now, the way you would differentiate is using the byte enable. So the byte enable in this case would equal 1, 0 because it's odd. And the byte enable in the other case would equal 0, 1. Now, for the SRAM chip, the addressing is actually half-word addressing. So each location in the SRAM chip is 16 bits. Okay, so this is 16 bits, 16 bits, so on, 4, 5, 6, okay. So this is address 0 in the SRAM chip, which refers to the address of this half word. So you can imagine there are 2 bytes in there. So in order to access, let's say this half word, the address line here would equal 3. Now, if you were just writing a byte, the lower byte, your address would be 3, and your upper byte, and because it's active low, will be a 1, and the lower byte would be a 0. So that's activating this lower byte in this address in the SRAM chip. So now, to give an example that maps across, if we wanted to write to, let's say, address 1. So we want to write to byte 1, or the byte address 1. So coming from here, your address would equal 0, and the byte enable would equal 10. Okay, that one maps to here, okay, which is part of the half word at address 0. So you need to translate that address to 0. Well, this might be a bad example. And then this byte enable would transfer to the upper byte and lower byte bits. So in this case, you're activating the upper byte and not the lower byte. Similarly, if we chose 5, 5 would be, so 0, 1, 2, 3, 4, 5 would be here. Okay, so this one maps to here, and the address is 2, and these would still be the same for those. Okay, so if we are converting each of these byte addresses on the left to the equivalent half word address on the right for the SRAM chip, this would be address 0, 0, then 1, 1, 2, 2, 3, 3. So you should see a pattern that's occurring there. Now, if this whole size here was equivalent to 512 kilobytes, then, and it was byte addressed, there would be 2 to the 19 addresses. But now, because in here we still have 512 kilobytes as well, but only every 2 bytes is addressed. So that is why you have 2 to the 18, or half as many addresses. That is a big hint. Okay. All right, so I think that's everything I wanted to cover to explain the SRAM, the part 2. So in order for you to test out that the SRAM is working, the assembly code is going to be very similar to the first part. However, now every single address in the address space has a unique location in the SRAM chip. So you probably want to do a write and a read from every address, which you can just do in a loop. But it's fair enough if you just want to do a very similar test as you did for the first one, making sure you test a number of different addresses and different transactions. With this interface, you can also do word transactions, so you should be testing store word and load word as well, which will operate by transferring 2 consecutive 16 bits. And yeah, that pretty much covers everything that I wanted to go through for this video. Okay, I lied. That was not everything I wanted to go through, or at least I thought of something else I can go through before ending this video. So just the block diagram for the final part, so for part 3. So for part 3, what you are doing is you are not changing any of the code in your SRAM controller module or your peripheral on external bus module. The code in that, if it worked before, should stay the same. So what you actually have now is you will have this being your, let's say, your SRAM controller module, and then you now have a second module, which is your peripheral on external bus module. Okay, and then the internal of the NEOS system looks very similar too. But now the difference is that this bus bridge here has now been increased in size. So whereas before it went from 0 to 0x7 f, now it has been doubled in size. So now it should go from 0 to whatever is double of that. I think it ends up being 0x. It becomes 5f's. Okay, so what you need to do now is you just change the top level module. The only changes you make are in the top level module. Well, you are creating the part 3 top level module, but by putting together the other 2 parts. So in your top level module, you create an instantiation of the peripheral, and then you create an instantiation of the SRAM controller. And now the connection to the external bus bridge needs to be split. Okay, so there will be signals that need to go to both of them. So some of them will just directly go to both, but others will need to, there's only one input for some of them. So for example, the acknowledge and read data, there is only one input for each of those back into the bus bridge. So you need to decide, or write some logic that decides when it is to take this, let's say that's the acknowledge, or when it is to take this acknowledge. So there should be some kind of switch that goes between those two. And the same for the read data. So there should be a switch between choosing the read data coming out of the SRAM controller or the read data coming out of the peripheral module. Now, how do you differentiate? Well, the suggestion in the lab sheet is to divide up the address space into exactly half. Okay, that means that the most significant bit is what you're going to be looking at to decide which particular module you're accessing. So I can't remember which one is given the lower half and which one is given the upper half, but let's say the lower half is given to SRAM, so that means if the upper bit is a 0, therefore you should be accessing the SRAM signals. If the upper bit is a 1, then you should be accessing the peripheral signals. So you should just have simple conditional statements in your top level module for part 3 that implements this switch functionality for those signals. The other signals are just duplicated to send to each of these modules. Okay. Now the other thing to keep in mind, if you have this double the size of address space, that means the address bits are now 20. It is now 2 to the 20, so there are 20 bits. But these modules down here still only take an address size of an address input size of 19 for the Avalon bus side. So you need to convert that 20-bit signal into a 20-bit address into a 19-bit address to feed into these modules. So I'll leave you to think about that. Yeah, so try and keep it simple. There's not much code to add to implement this last part for the Verilog. And the assembly shouldn't be too hard either. So once again, your assembly code should test all of the same sorts of operations that it did before, but now testing locations in the peripheral that is mapped to one half of that address space and the SRAM, which is mapped to the other half.